Welcome to this explainer. Today, we are taking on a massive, honestly pretty intimidating challenge. We're doing Docker in 7 minutes. But listen, we aren't just going to skim the surface and look at basic terminal commands. No, we are going to aggressively strip away all the magic of Docker to look at the raw, ultra-deep Linux kernel primitives that are actually powering it under the hood. So get ready for a seriously ultra-detailed deconstruction. Let's jump right in. Let's kick things off by completely shattering an illusion right out of the gate with this incredibly provocative truth from our source material. There's no such thing as a container. Not in the Linux kernel anyway. Seriously, there is literally no single container system call or magical container data structure living in your operating system. It's a total myth. So, you're probably wondering, if it's not a native kernel object, what exactly are we running? Well, when you strip away all the slick branding and marketing, a container is simply a standard Linux process. That's it. The whole shebang is just a normal process, but one that's been isolated, constrained, and monitored by two absolute powerhouse kernel primitives, namespaces and cgroups. Literally everything else you know, the images, the layers, the runtimes, is just fancy tooling built entirely on top of these two pillars. Okay, let's dive into this and establish the physical laws of our isolated universe down at the absolute lowest kernel level. First up, namespaces. Think of namespaces as putting a very strict set of blinders on a horse. They dictate exactly what resources of the host operating system your containerized process is allowed to see. For example, the PID namespace completely tricks the container into thinking it's running process number 1. Then we have the net namespace, which gives it a totally isolated virtual network stack, the MNT namespace for hiding the host's file system, and there's even a time namespace to isolate clock offsets. It's essentially brainwashing a Linux process so it thinks it is entirely alone on a server, even though it's happily sharing the underlying hardware with dozens of others. Now, while namespaces isolate what the process can see, cgroups govern what the process can actually use. They enforce the physical limits of memory and CPU. And it's really important to note the evolution here. Version 2 of cgroups vastly improves upon the fragmented, honestly kind of chaotic multiple hierarchies of version 1. Instead of different resources fighting each other, cgroups version 2 gives us a beautiful, unified, single hierarchy. This is the exact mechanism that guarantees predictable, multi-tenant safety, ensuring that one rogue, memory-hungry container doesn't accidentally eat all of your server's RAM. All right, so now that we know the core primitives, let's move up the stack and break down the incredibly decoupled architecture that actually executes your commands. Imagine typing a simple Docker run command. Where does it actually go? Well, this sequence perfectly maps out that journey. First, your command line fires an API request to the Docker daemon, known as Dockered. Then, the actual heavy orchestration is handed off to containerd, which acts as the core supervisor. Next, containerd spawns this highly specialized, lightweight little process called a shim, which finally invokes runc. Now, runc is the absolute lowest level engine here. It interacts directly with the kernel to configure all those namespaces and cgroups we just talked about. It spawns your process, and then boom, it immediately exits. Wait, if runc just bails, who's watching your container? Enter the loyal containerd shim. Since runc exits, this shim stays alive specifically to babysit your container. It acts as what's called an OS subreaper, meaning it adopts orphaned processes to keep your system clean. It captures exit codes, it keeps standard input and output streams open so you can actually read your logs, and crucially, it enables live daemon restore. That means the main Docker daemon can entirely crash, or you can restart it for an upgrade, and your containers will just keep humming along uninterrupted because that trusty shim is holding down the fort. Next up, let's talk about the physical manifestation of containers on your hard drive. We're looking at union file systems and overlay 2 storage. You might be wondering, how on earth do we store all these massive container images efficiently? It's all thanks to the overlay 2 architecture. Picture it kind of like a layered cake. At the absolute bottom, you have the lower dir. These are your immutable read-only image layers. Sitting right above that is the upper dir, which is a single read-write layer allocated specifically for your active container. Finally, the merge directory is the unified, seamless view the container actually experiences. This brilliant setup is exactly how hundreds of running containers can safely read the exact same static base libraries from the lower dir without duplicating a single byte of data on your actual disk. And this layered approach is exactly what enables the famous copy-on-write mechanics. When a container just needs to read a file, it happily pulls it from the read-only lower dir. But if it needs to modify that file, the system springs into action with copy on write. It finds the file, copies it all the way up the stack to that mutable upper dir, and then executes the write up there. This perfectly explains why modifying a massive file for the very first time inside a container incurs a slight little latency hit. The kernel is literally physically copying it up the stack before it lets you touch it. Okay, but here's a brain teaser. What if you want to delete a file? Because the lower layers are strictly read-only, you literally can't delete inherited files. So instead, the system uses a genius little trick called a whiteout file to render them invisible to the container. It essentially writes a special empty marker, a character device, to the upper dir that acts like an invisibility cloak, masking the underlying file. When that unified view is presented to your app, the file simply appears to be gone, without the base image ever actually being touched. Now remember that upper dir is completely ephemeral. The second your container is deleted, poof, the upper dir and all its data are destroyed. So when you need true rock-solid data persistence outside that ephemeral layer, you have to look at volumes versus bind mounts. Bind mounts rely on specific hard-coded host paths, which can get super messy and platform-dependent really fast. Volumes, on the other hand, are the undeniable production standard. They are entirely managed by Docker, they offer high performance, and they're completely cross-platform, making them absolutely perfect for things like your critical databases. All right, let's switch gears. An isolated process isn't much use if it can't talk to the outside world, right? Let's map out the virtualized network topography. Think of this as Docker acting as a master electrician, wiring up a virtual cable system right behind the scenes. Inside the container, you have a virtual interface, ETH0. Docker then creates a virtual Ethernet, or VETH pair, to literally bridge the namespace gap. One end goes inside the container, and the other end plugs into the host's software bridge, usually called Docker 0. And when you publish a port to the outside world, Docker dynamically injects NAT rules into your IP tables to translate and route your traffic. It is quite literally building a complex virtual switchboard inside your Linux kernel. But listen, how you set these networks up really matters. The default bridge is just IP-based, and honestly, it's completely unisolated. But user-defined networks, they are a massive upgrade. They embed a custom DNS server so your containers can easily find each other by name. But more importantly, they enforce strict, safe isolation boundaries using those IP tables. This is the exact reason why a noisy, compromised neighbor container doesn't accidentally crash your secure production database. Finally, let's zoom back out. This is the climax of our deep dive, where we get to completely reimagine what a container actually is. Because Docker's architecture is totally decoupled and the runtime engine is entirely pluggable via that container gem we talked about, it begs a massive question. If Docker is just an orchestration chain, what happens if we totally swap out the runc layer at the absolute bottom? Actually, it turns out we don't even have to use standard Linux processes to run our code anymore. That's right, we can seamlessly yank out runc and swap in entirely different paradigms. You could use Kata containers to launch lightweight hypervisor VMs, giving you true hardware-level isolation. You could drop in gvisor for highly secure, unprivileged kernel sandboxes. You can even plug in WASM time to get the raw, blazing speed of WebAssembly execution. And the craziest part? You get to do all of this while using the exact same Docker CLI commands you already know and love. Which brings us to the very end of our ultra-deep 7-minute dive into Docker's architecture. And I'm going to leave you with this final provocative thought to chew on until our next explainer. As WebAssembly runtimes and these hardware-level hypervisor emulators continue to mature and plug so cleanly into this ecosystem, will the traditional Linux container as we know it today actually become obsolete in the next decade? It's a wildly fascinating paradigm shift to think about. Thanks so much for learning with me.